So in problem 1629, we're asked to do something a little different. This time we need to provide the reagents needed to accomplish each of the following transformations. So part A, we have this molecule here, this alcohol. We convert the alcohol to the aldehyde. That we can do this, this is simply an oxidation. The convenient way to do this oxidation would be pyridinium chlorochromate. I think we could also do this with a Swern oxidation. But this pyridinium chlorochromate I think would work. Part B, we have this aldehyde. We convert to this tertiary alcohol. This alcohol has a methyl group and an ethyl group attached, and so we can do this using Grignard reagents. Let's begin with the ethyl group. So ethyl magnesium bromide. Whenever we do a Grignard reaction, we have to include an acidic aqueous workup. So that's parts 1 and 2. Part 3, in order to do our second Grignard reaction, we need to convert that alcohol back to a carbonyl, and we can do that with PCC. And then part 4 will be our Grignard reaction with methyl magnesium bromide, CH3 MgBr, and another acidic aqueous workup. So that would be a 5-step reaction in order to add this methyl and ethyl to our aldehyde here. Part C, we have this alkene, and we convert it to a cyclic acetal. And so the first step will be to get a syn dihydroxylation, we need this on the same side because both of these oxygens are pointing down. So the first reaction to get that syn dihydroxylation, we need to oxidize that alkene using osmium tetroxide. That's OS, not O5. Okay. So the osmium tetroxide will add the hydroxyl groups on the same side of the double bond. Once we have those two hydroxyl groups, then we can react with benzaldehyde. With catalytic acid in order to form our acetal. Part D, we convert this alkene to this cyclic acetal that we can essentially convert this alkene to a carbonyl as our first step using ozonolysis. So the first step of ozonolysis is to react that with ozone, followed by dimethyl sulfide, CH3SCH3, and that will that will convert this to a carbonyl. Then once we have the carbonyl, we can react this with 1,2-diol with catalytic acid again to form our cyclic acetal. So part E. We have this alcohol and this epoxide ring. We need to form this 6-membered cyclic ether with this alcohol. And essentially this is an intramolecular epoxide ring opening that we need to decide, does this alcohol attack the most hindered side or the least hindered side, because that will determine whether we use acid catalyzed ring opening or base catalyzed ring opening. And so if the alcohol were to attack our most hindered side, so that would be acid catalyzed ring opening, then we'd wind up with 1, 2, 3, 4, 5, 6 atoms in that ring. If the alcohol were to attack our least hindered side, then we would wind up with 1, 2, 3, 4, 5, 6, 7 atoms in the ring. We want the 6-membered ring, so we need to attack our more hindered side. So we'll just say catalytic acid, and that should do it. That we protonate the epoxide here, and once the epoxide is protonated, then we can use the hydroxyl to attack the most hindered side, opening up that epoxide ring, forming this 6-membered ring, and producing this alcohol. part F, start with cyclohexanone. We produce the cyclic thioacetal. And we can do this using a 1,2 dithioether, not thioether, dithiol with catalytic acid. Oh, I should actually put that on the screen. Part G, we have this ketone. We want to produce this hydrocarbon, so we just want to get rid of that carbonyl. We could do this with a Clemmensen reduction, a Wolff-Kishner reduction, or a Mozingo reduction. Let's just say we want to do this with a Wolff-Kishner reduction. And that would be the reaction with hydrazine, potassium hydroxide, and heat should do it. And part H, so we want to convert this ketone to an ester. That we want to put that ester, this oxygen, on the side with the phenyl ring. So this is a Baeyer-Villiger reaction. We would use metachloroperoxybenzoic acid as the reagent. So that is 1629.